What's up, Math 1 students? It's Mr. Rabins, and we are going to just go over a couple of notes to help you out with the 1.4 Ready, Set, Go. So, here we go, function notation. This should be a little bit of review. I believe this was in one of Ms. Gragnani's videos, excuse me. Function notation. The big idea here is that we now don't use this idea of y. We use maybe f of n or f of some variable. All right. The big idea with this, the important thing, is that we understand that this n is going to be our input. All right. Whatever number we see in there is the input into our function. And when we plug everything in and we get the result, that is our output. And so really, I should actually mention, this whole thing becomes an output as well, right? These two are hand in hand. If the n is the input, f of n, the whole thing, is the output. And so when we go to this example over here to the right, hopefully we notice we have our function. This is our f function, and we know that it is in terms of x. 2x minus 3. F of x is equal to 2x minus 3. So when we see f of 4, we notice that 4 is the input. And what we are going to do is we are going to input or place it anywhere where we see the x variable. So I see a 2, parenthesis, minus 3. And of course, I replace the x with what I know my input is, or 4. Now, we have 2, parenthesis, 4, minus 3. So when I go and I get this result, all I do on my calculator is I do 2 times 4 minus 3, or 8 minus 3, and we get our output is 5. All right, easy enough. That should be review. We're going to continue practicing those. Let's kind of go over something that we need to, that's going to kind of work off of our last task from 1.4. And it should be like a continuance of our understanding of arithmetic sequences. So let's see what's going on here. All right. As we look at this, when we look at A, this gives us a sequence, 2, 6, 10, 14, 18. And I would say that we probably could right off the bat see what's going on here. Is this an adding pattern? Is it a subtracting pattern? Multiplying? Dividing? Well, hopefully as we go and we look and we test some things out, we notice that if we add 4 to 2, we get to 6. And if we continue adding 4, we keep getting the next term of our sequence. And so with that in mind, we should be able to answer a couple of things. First of all, we should definitely be able to come up with our next 3 terms. If we continue adding 4, 18 plus 4 is 22, plus another 4 is 26, and lastly, one more 4, we get to 30. All right, so absolutely we can write the next 3 terms of this sequence. We also should know the common difference. This is an adding pattern. It's arithmetic because we're adding the same or a constant each time, which we call the common difference. Because we're adding 4 each time, I'm going to say that my common difference is positive 4. I don't know if you need the positive. I just like to put that there so we know that we're adding the 4 rather than subtracting it. Now, in terms of recursive and explicit, we kind of need to go back and we need to read the instructions here a little bit. We want to write our recursive function and an explicit function for each sequence. We want to circle where you see the common difference in both functions. Here's the big thing right here. The first term is the first term, not the 0th term. So what I'm going to do here, I'm going to make a quick little table. And I'm going to say that my term values are n, and the output values are f of n. Okay. So here's the problem, and I shouldn't say problem, but what's different from what we were kind of used to. Usually we start here at 0, okay? But now what we're doing, it's telling us the first number, this 2, is actually the first term. So I have to start with 1, and then my second term is 6, my third term is 10, my fourth term is 14, and I'll put one more. My fifth term is 18. We could keep going, but we don't necessarily need to. I think this is enough for what we need. So let's see here. A lot of you guys are getting really good at this. We see that to get from 2 to 6 to 10 to 14 to 18, and we actually already did it up here, we're just adding 4, right? We're adding 4. We're adding 4. We're adding 4. And so that is where our common difference comes in. We're adding 4 each time. Now, if you remember correctly, we're adding 4 to the value or the term before it, right? So I needed to have the 2 to get to 6. I need the 6 to get to the 10, etc., etc. And so when we talk about this recursive idea, and I want to try to write my f of n function, well, the problem is I actually need what's above it, all right? I need f of n minus 1, because what do I need to do to it? I need to add 4. And so to get f of n, I must have f of n minus 1, and I have to add 4 to it. All right, and so I'm going to come over here in my recursive function. I'm going to say that it's still my current term equals the previous term plus 4. And then if you remember with recursive functions, we always have to give it that starting point. And so this is another difference between what we've been doing kind of prior and now today with having the first number be the first term. The very first value, or the starting point, is no longer f of 0, right? If you notice, we're starting at an n value of 1. All right? And so what I'm going to have to do is I'm going to have to say that the first term, which is at 1 this time, is equal to 2. Again, only real difference between this and what we've done prior is that in previous problems that we've done, the recursive has been f of 0, but we don't have f of 0, we have f of 1. All right? Now, to kind of work off of and get this explicit function, there's a couple of things to do. What I'm going to do is something that we've kind of done in class through our tasks, and I'm going to say, well, at time or at term 1, the function value is just 2. But at time 2, how else can I write a 6? Well, I can write it as 2 plus 4. And how about 10? Well, I can write that as 2 plus 4 plus 4. And 14? And 18? And on and on and on. And so what we're going to do is we're going to clean this up. We're going to make this look a little bit more like an equation, or actually I should say an expression, excuse me. I know that this 2, if I keep going along, this is 2 plus how many 4s? How many 4s did I add? Oh, I added 0. How about here? Well, I see 1 4, so I added 1 4. Here, 2 4s. And on, and on, and on. And this can keep going. But here's the thing. We need to come up with this rule right here. Okay? We need to know at term n, what is our explicit function. And this is where I need you to kind of notice that there's a difference. There's a key difference in what we just did here compared to what we've done previously. And what I want you to do is I want you to look at these numbers, and I want you to look at these numbers. Oh, shoot. Bad job, Mr. Ravens. Okay, hopefully you guys can still see that those are all 4s. Well, what do you notice? What do we notice about this 0, this 1, this 2, this 3, this 4? in comparison to the term number. Oh, wait a minute. These are all just one less. And how do we say one less than the term number? How do we say that, but kind of in more mathy language? Well, we've been talking about it in class, so hopefully this idea makes sense. It's just the current term number take away 1. And so what we're going to do to come up with a general rule for n is, hopefully you guys notice this 2 is still good, right? This 2 doesn't go away. But now, instead of adding a 4 for each term number that we're on, we're going to multiply it by n minus 1. And so this is what we're really caring about with our explicit function. We're going to have f of n equals 2 plus 4, but instead of multiplying it by n, we're going to multiply it by n minus 1. And so, to kind of go along with this idea of circling where you see the common difference, hopefully we see it right here, and again, we see it right here. Alright, let's do one final thing. I know this video is getting a little long, shoot. I do want to show you one other thing that can help you get to the explicit function a little quicker. Alright, so what I'm going to do is I'm going to recreate this table. I'm still going to go n and f of n, and I'm still going to put what I got. I got 1, 2, 2, 6, 3, 10, 4, 14, 5, 18. I know I went a little quick there. But if we want to kind of forget about this n minus 1 idea, what we can actually do is we can almost create the 0th term, almost go backwards one space. And so what I'm going to do is I'm going to add in a 0th term, and I'm going to use the opposite. I knew that I was adding 4 to get from 2 to 6 to 10 to 14 to 18. Well, what do I have to do if I want to go backwards? Well, I do the opposite. I take away 4. So this is actually negative 2. And now this actually turns it's a little closer to what we were doing previously. Whereas now, what do we have here? I have a negative 2. How can I rewrite 2 in terms of my starting value and my common difference? Well, it's negative 2 plus 4, or negative 2 plus 4 plus 4, or negative 2 plus 4 plus 4 plus 4. And the idea here is, now do you notice that the number of 4s, or the number of common differences, is the exact same thing as the term number, as the 1, the 2, and the 3? And so what we can do here is, if our term number is n, we now can use the new kind of starting term, or like the one at the 0th term, so negative 2. But now, instead of adding the n or n minus 1 4s, we're actually adding the exact same number of 4s as we see as the term number. So here I added 1 4. Here I added 2 4s. Here I added 3 4s, because that is the exact same thing as the term number. So, lastly, we could also, and both of these are perfectly acceptable answers, guys, could give that function as well. And lastly, there again is that common difference. Alright, so I know this video was a little bit long, but I hope that it made sense in terms of getting to our explicit formulas as well as the recursive functions.